NanoVNA is a powerful tool for tuning antennas, making them more efficient and effective. This video provides a beginner-friendly guide to using the NanoVNA, covering the basics of antenna tuning and how to get the best results. Unlike tuning using your radio, you do not have to transmit a significant signal on the air. NanoVNA uses tiny signals on 101 frequency steps in the chosen range and measures the reflected energy from the antenna. That gives you a graph of SWR pattern in the frequency range and tells you the resonant frequency of your antenna. There is absolutely no risk of damage to your radio, as can occur by transmitting on a frequency with high SWR. Once you know the resonant frequency, you can either lengthen or trim your antenna elements to get best resonance on your desired frequency range. All my antenna projects need this device to optimize performance. It can also probably do more, but I have to check it out. Here is the video on unboxing my new NanoVNA. As mentioned on the box, it is a very tiny handheld vector network analyzer. See what is inside on unboxing my new NanoVNA. There are two sets of USB cables. One is USB Type A to USB Type C, which I use for charging. The other cable has USB Type C connector at both ends. That is useful for the current type of chargers with only USB Type C sockets. There are a couple of SMA to SMA jumper cables and a few connectors. One can use the SMA connectors while calibrating the NanoVNA. There is a strap for holding the device in the hand and a short leaflet. The leaflet shows NanoVNA menu structure map. It shows the various menus and sub-menus. Here is the reverse side after unboxing my new NanoVNA. It shows three frequency ranges, 50 kHz to 300 MHz. As previously discussed, that is the fundamental oscillation frequency of NanoVNA. Next range is 300 MHz to 900 MHz. This range uses the third harmonic of the fundamental frequency. Finally, there is 0.9 GHz to 1.5 GHz, which uses the fifth harmonic. Power needed is 5 volt USB, 500 mA maximum. It has a built-in rechargeable internal battery as well. Here's a special caution note. Avoid static discharge. This is a delicate instrument which has to be handled with extreme care. This is the USB Type A to Type C cable which I use for charging the internal battery of the NanoVNA. I use my mobile phone charger as a USB power source. Yet another USB cable with Type C connectors at both ends. Newer mobile phone chargers do not have Type A socket. Use this cable with those chargers. Here we have the NanoVNA along with two short SMA male to SMA male jumper cables. These can be connected to SMA female connectors on devices to be tested. Use with caution as SMA connectors may get damaged with rough use. You can fix the NanoVNA in your hand with this strap. The small triangular piece is for accessing the menu. This is the calibration kit. SMA load 50 ohms, SMA short and SMA open connectors. In addition, there is an SMA male to SMA male barrel connector as well. This is the view of SMA connectors from the other end. Main body of the NanoVNA with two ports on one side. A peel-away polythene sheet protects the screen. You can see port 1 and port 2 well now. S11 is used for measuring SWR. During SWR measurement, RF energy from the oscillator is transmitted. Then reflected energy is compared to the forward energy. S21 is used for measuring insertion loss of a length of coaxial cable. In that case, the transmitted output level is compared to the level received by the receiver. Sliding switch to turn the NanoVNA on and off is near the USB Type-C socket on top side of the device. Blue LED keeps on blinking when the power is switched on. Red LED lights up during device charging. This is a multi-function switch, a rotary switch. You can press it to open the menu and slide it to either sides to execute commands as well as to shift the markers. Usually I was accessing the menu using a stylus on the front panel, but now you'll see this is another way of accessing the menu. You can see that the menu has come by pressing the multi-function switch and moving across the menu by pushing the switch to the right. It moves this way, and if I want to move the other way around, I will move the switch in the opposite direction. Now if I want to select that and execute, I just press it. See, it has gone to the next menu. You have selected trace, and then if you press, it will execute so that this next sub menu is seen. Now I am showing how the same switch can be used to move the markers. This is the marker you can see. See, I am moving the marker towards the right side. I can move it the other side also. Now you can see that the marker is moving the other side. How do we activate the traces and remove them? We'll see. First we'll activate the menu, and in the menu you can see you choose display, and in display you choose trace. Now you can see that there are trace 0, 1, 2 and 3, 4 traces. So I'll press on 1, trace 0. So a yellow colored trace has been activated. Press again on trace 1, another trace on the lower part of the screen has been activated. Now the Smith chart like tracing, trace 2 you can see, then the pink colored tracing has come when I pressed trace 3. Now I'll try removing these back to the original position. One trace gone, another trace gone, still another gone. Now no traces at all. That is how you bring in and send away the traces in a NanoVNA. Before calibration, you have to set the frequencies, start and stop frequencies. You can see the default setting here. The start frequency is 50 kilohertz and the stop frequency is 900 megahertz. So you'll have to change it. I am going to test my multi-band fan dipole antenna. That antenna has elements for 40 meter, 20 meter and 10 meter. They are all parallel and mounted in an inverted V fashion. It also functions on 15 meter as 15 meter or 21 megahertz is the third harmonic of 7 megahertz or 40 meter. I have just switched on the NanoVNA, and what I am going to do is that I am going to remove all those traces because that causes clutter on my screen. So what is left is only a single trace. That single trace is SWR. Now it is on SWR mode. I'll change the scale because scale is 250. I want checking with 1. So SWR will be 1:2. So much SWR will be shown. I am setting the frequencies. On display, start frequency is set at 6.5 megahertz. You can see 6.5 megahertz has come here. Again, same process. Stop frequency I am keeping it 29 megahertz. This is 29 megahertz. I will be connecting using this jumper cable. This has a SMA male connector at one end. This is another SMA male and an SMA female to female adapter also. Cable has been connected. Now I need to connect an SMA open connector. This is an SMA open connector. I am connecting it here. Now we will go for the calibration. Calibrate. First you have to reset the calibration. It has been reset, and calibrate. I am first calibrating open, SMA open. SMA open has been calibrated and it has moved to SMA short. This is the SMA short connector. I have connected the SMA short connector. Now again calibrate the SMA short. It has been calibrated. You would have seen a blue line running and the tick mark has come here. Now the SMA load, 50 ohms load, this is having a silvery color that is being connected. SMA load has been connected, and for calibration again you press on SMA load. Again a blue line had been seen and tick mark has come. SMA load also has been calibrated. Now I'll just move through isolation and done, because I am not using all those for this SWR measurement. Back. I'll just recall and see. Actually I have not saved it. I will better save it to the SD card. Save calibration. I give another channel 3. The other channels I have used earlier. So save to calibration 3. Now I will recall. Load from SD card. calibration 3 has been recalled. You can see the range is seen here. 6.5 to 29 megahertz is the range. Now only the SMA load has been connected, and you see SWR is 1.024. that is for the dummy load, SMA dummy load. I have set the start frequency and stop frequency here. Stop frequency is 4 megahertz. I am trying to save it. See, fail write. That means it cannot be saved. Reason is that there is no SD card inserted in this NanoVNA. This is a 32 GB micro SDHC card. Now the card has been taken out of the plastic pouch. This is the SD card slot on the lower part of NanoVNA. The SD card has been partially inserted, and I am going to press it down. Now the SD card is inside the NanoVNA. Now I am going to save the calibration. Save to SD card. See, it has been saved to SD card. The NanoVNA has been switched off, and I'll switch it on again. You can see that the calibration has gone back to the previous situation. You can see 50 and 900 here. So you can load the calibration saved in the SD card. You can see, you choose SD card and load calibration. This is the calibration which I have stored. You can see it has come as 3 to 4 megahertz. That is what I had initially stored. So it has come right here. So that's how you store information in the SD card and load it back. Now I am going to connect the multi-band antenna. This is the PL259 from the multi-band antenna. It is being connected here. You can see that there are 4 dips in the SWR and highs also. This is one dip in SWR. This is a very high region here. Another dip, still another dip. Now we will use the marker from this multifunction switch. Marker will be rotated to correspond to the minimum SWR. This is the minimum SWR I am getting, that is at 27.425 megahertz. You can see the minimum SWR on this band, that is 27.425 megahertz, that is 1.18. So in the 10 meter band it is resonating below the amateur radio band. So there will be higher SWR when I go into the actual amateur band. You can see 28.1, the SWR is 2.258, but that will be tunable with my FT710 radio. Still the SWR is not exactly at the resonance point of the. Now I will see the next band in which it is resonating. Again the minimum SWR, almost the minimum is 1.359 on 21 megahertz. That is the lower end of amateur radio band. That is good for me to operate CW on 15 meter. If I move higher up, SWR is increasing, but that is beyond the amateur radio band. Anyway, at 21 megahertz it is 1.349. That's good for me for operate CW. This is again on 14 megahertz, 20 meter band, 14150, excellent SWR, 1.163 at 14.150, the old AirNet India frequency. Now we have AirNet India on 7150 megahertz. So again, resonance on 20 meter. You know, this is a multi-band antenna, so you see resonance points everywhere. This is on the primary band, that is 7 megahertz. SWR is 1:2 at upper end of the band. You know, this is 7.175. It is near the upper end of 40 meter amateur radio band. And if I go lower down, SWR is very high, but that is below the amateur radio band, 6.95. So it is 1.2 at 7.175, upper end of amateur radio band. This I can very well tune with built-in antenna tuner of FT710, which has a range up to 3 of SWR. So you can see the nice pattern, 4 dips in SWR for a multi-band fan dipole antenna. There are elements for 3 bands and it is resonating on 4 bands, covers major amateur radio bands. Now I can trim the antenna or lengthen whatever is required to adjust SWR on various bands, but that is going to be a laborious process. I have to bring down the antenna each time, trim or extend, and then check the SWR and remount it. But practically for me, this is good enough because all the SWRs are within the tunable range of my radio, so that I need not worry too much. That's all I would say. For ideal situation, I have to do that tuning of the antenna.